The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
I'm going to talk about some considerations in application of the miniature concrete prism test in evaluating ASR potential of job concrete mixtures. Inamur Latifi and Sai Sudhir Reddy, my graduate students who've been working on this project. And I'll just acknowledge some of this work started off with funding from Federal Highway Administration, and then we had some funding from Portland Cement Association, some help from Lehigh and Argos for some materials, and a number of different aggregate suppliers provided aggregates for our studies throughout the course. So just give you a brief overview of this presentation. I'll be very brief on reviewing the existing test methods. My previous speakers have already done a good job of those methods and some issues, so I'll be very brief on that. But I'll mention a little bit about the miniature concrete prism test itself, what this test method is. And I've spoke about this method in previous ACI meetings. So again, I'll try to be very short, and I'll focus a little bit more attention on different factors that distinguish the labcrete from realcrete and how some of those impact ASR testing aspects. And also I'll briefly talk about some experimental investigation we've done to look at the role of different concrete mixture proportion variables and how they influence ASR expansion, and how we can use some of this knowledge to perhaps start looking at job mixtures and assessing their potential for ASR. And finally, I'll have some conclusions from this talk. As was previously discussed, there are a number of ASTM test methods that look into alkali aggregate reactivity, whether it's ASR or alkali carbonate reaction, but I just have a list for ASR here. The 227, the 289, 295, these are some of the earlier tests. The more popular, ASTM Z1260, the motor bar test, 1293, the concrete prism test. And for ACR, we have a few other tests that are C295, the 586 rock prism test, and the 1105, the concrete prism test. As Mike pointed out earlier in the first presentation, and as well as Soleil, there are a number of issues with some of these existing test methods, particularly the two popular methods that are widely used, the 1260, the motor bar test, and the concrete prism test, which is considered the more reliable of all the test methods. But still, we just spent last two presentations talking about how alkali leaching can impact some of the results of the concrete prism test. And certainly the motor bar test, which is a faster test, but you have issues with crushing aggregates down from coarse aggregate size to fine aggregates, and doing that, you change the reactivity of aggregates dramatically. Most of the aggregates, you tend to increase the reactivity with a decreasing particle size. But there are certain kinds of aggregates that actually show the reverse trend, where with crushing it finer, you lose the reactive component and you end up less reactive with crushed material than the coarser material. So all of these manipulations that we do to fit into our test methods alter how aggregates show up as being reactive or not in the real field structures. So the miniature concrete prism test, which is now an AASHTO provisional standard, was embarked upon to address some of these challenges that we have with the existing test method. These are some highlights of this method. Basically, this is a concrete prism test, so there is no significant aggregate crushing involved as far as coarse aggregates, although the maximum size of aggregate that's used in these tests is only about a ½ inch maximum. There's no alkali leaching issue involved in this because of some of the soak solutions that we use in this test method, and I'll talk about how we can adopt some of these soak solutions for job mixtures where the potential alkali loading is different than a standard test method, and how we can address those issues. And also, we get results from this test fairly quickly, in only about 56 days or 8 weeks for a vast majority of aggregates, and for certain slowly reactive aggregates, we may have to wait a little bit longer, up to 12 weeks, to look at certain expansion trends and predict how they might behave in the long term. In developing this test method, by the way, the miniature concrete prism test, this was calibrated against the concrete prism test. So to the extent that the concrete prism test has issues, right now at the present moment, that is the best test we have. So this test method was developed with an intent of trying to have a faster version of concrete prism test. So that was the intent of this method. So keep that in mind as I go through the presentation. In this test, we could look at both ASR, ACR issues and look at both aggregate reactivity as well as looking at mitigation measures, their effectiveness, and finally, potential to look at job mixtures as well, which I'll talk about today. Just to give you an overall idea of what this method is, essentially it's very similar to the concrete prism test. You make concrete prisms with cement contents of about roughly 420 kg per cubic meter. The cement alkali loading is you start off with the high alkali cement and you boost it up to 1.25%. And the water cement ratio that is used in this study is about a 0.45. The coarse aggregate volume fraction is limited to about 0.65 as a dry rotted unit weight volume. And these specimens, there's sort of a hybrid of 1260 and 1293 test methods in that these samples are soaked in a 1 normal sodium hydroxide solution. And the justification for that, at least for this particular recipe, is that when you have a high alkali cement that's raised to 1.25% with a water cement ratio of 0.45, what you end up in the pore solution of the concrete specimens is actually about exactly equal to about 1 normal sodium hydroxide solution. So the alkalinity in the concrete itself is very similar to what you're soaking it in. So for a standard test method, they actually match up quite well for the alkalinity. And these are stored at 60 degrees Celsius. Again, as we discussed before, really, we can't afford to wait a year or 2 years with concrete prism tests, and one way to accelerate it is to bump up the temperature. And the question is, why 60 degrees Celsius? As it turns out, like I was pointing out earlier when Mike's talk was, if you look at the average temperature of concrete pavements throughout the country, it's not at all uncommon that some of the concrete temperatures in peak summer get up to upwards of 55 degrees Celsius and higher. So 60 degrees Celsius is really not all that unrealistic if you look at the temperatures that some of the concrete structures are exposed to. Granted that there are certain issues with silica solubility and how they vary, but from a practical standpoint, this is a temperature that's quite reasonable in my view. I'm not going to get into the details of it, but one thing we noticed too is that at 60 degrees Celsius, you actually start destabilizing some sulfo-aluminate phases. Some of the ettringite goes into solution, and that affects your alkalinity. So having a soak solution of 1 normal sodium hydroxide acts as a buffer to compensate for some of the alkalinity changes that happen if you didn't have a soak solution. So that also was one of the findings from our preliminary studies. So the specimens that we use for the study are a 2 by 2 by 11 and a quarter. That's 11.25, not 75. But basically, they look like your CPD. They're soaked in a solution and maintained at about 1 normal sodium hydroxide, 60 degrees Celsius. And we kind of go through the initial process of letting them cure in water for a day and then subsequently storing it in sodium hydroxide solution. And the idea there is that even within that first day of curing in water at 60 C, you essentially gain sufficient mechanical strength in these specimens that they're able to actually resist some of the expansive stresses that build up later on due to ASR. And we take readings periodically all the way up to 56 days for most of the aggregates, but some cases we go up to about 84 days. And when you're testing aggregate in this particular method, use a non-reactive sand if you're testing for coarse aggregates and vice versa to study how they behave. So just to kind of give you a comparison of sample sizes, these are essentially a motor bar, an MCPD sample, and a concrete prism test. And otherwise, the test is very similar to other methods, so it's very easy to run. Everybody's familiar with how to do 1260, 1293. The MCPD is no different from that standpoint. In the original scope of the study, when we initially did this, we looked at about 33 different aggregates from throughout the country that had some established field performance. And of those, about 12 aggregates, we had good data in all the 3 methods, so we could do some comparative work. And we also looked at about roughly 20 different SEMs and how they mitigated different proportions. So I'm really not going to talk too much about those individual results, but I'll just share with you general findings. So these are those limited aggregates where we had all different data from all the methods, and we found that basically the MCPD at 56 days correlates really well with the concrete prism test at a year. and both coarse and fine. But when we selected these aggregates, a lot of these aggregates were either highly reactive or non-reactive. We had a very few that were in between. More recently, we just finished an extensive study looking at 26 different aggregates that were essentially all borderline aggregates that were between 0.1 and 0.2% expansion in 1260. So these are typically your false positives and false negative aggregates where you get a lot of confusion as to what is their reactivity. We just finished that study. I'm not going to share those results here as the focus of this is about the job mixtures. We have another presentation in open paper session tomorrow that talks about those issues, so you can listen to that. But this is the correlation between the CPT and the MCPT. They correlate very well. When we did the correlation with the motor bar test and MCPT, the scatter was quite significant across all these aggregates. So clearly, the miniature concrete prism test is alternative to concrete prism test with a much shorter duration, and you get results that are very comparable with the CPT. So based on that study, we developed a guideline as to how the reactivity can be assessed. This is a table that talks about, different moderately reactive or highly reactive aggregates or very highly reactive aggregates. But there's also another category here of a slow or a low reactivity aggregates. These typically tend to fall below the 0.04%, but their rate of expansion beyond, that is from 8 to 12 weeks, seems to be different than aggregates that are truly non-reactive, and that's where we make some distinctions. So there's a lot more data now that we have with these new materials that we tested recently. This criteria seem to hold good for those aggregates as well. When we did all the mitigation work, basically what we found was that even SEMs can be evaluated in a fairly short duration, although the expansion criteria are much tighter for those, considering really in CPT it takes 2 years. Here we're only trying to limit it to 56 days or 8 weeks, but the thresholds are lower with SEMs. And we also did a multi-lab round-robin test to look at what the variability of this test method across 4 different labs. And what we found was generally at higher levels of expansion, the coefficient of variation was quite small, but as we got to really the borderline, the limits of thresholds, the correlation went up to about a little over 10%, 12%, which is still not too bad considering what this test method is. And we have more data, and certainly a much bigger round-robin study needs to be done to see what the variability of this test method is. So like I said, this method is right now an AASHTO provisional standard, TP 110, that's in the books. It's all laid out if anybody's interested to take a look at this method and follow this method. So that sort of lays the background for us to look at the job mixtures. One of the big differences between the standard test method and a job mixture is that the concrete mixture recipes or the proportions are very different. And if you look at every other test that we do on concrete, whether it is compressive strength, flexural strength, or even durability tests like chloride permeability, we actually test concrete that is going to be placed in the field as is. ASR is one of the few tests where we actually have tests on a recipe that has nothing to do with what's out in the field. And yet we put all the eggs in one basket and say, this is how it works or it doesn't work. So what I tried to do in this study was to look at what are different variables in field concrete that we are not capturing in the standard test method. So we kind of tried to look at the effect of different components. So we looked at effect of water-cement ratio. We looked at total cement content. We went from 600 to 800 on the lower side as well for certain paving mixes and so forth. We looked at alkali loading levels in concrete from really low alkali to really high alkali, and look at SEM dosages and volume fraction of coarse aggregates to account for any variability in the mix designs. And some of these results we try to explain in terms of the pore solution alkalinity that develops in each of these mixes and how it relates to the expansion that we observe. I'm going to go through some of these individual parameters here, but here is basically an MCPT test. What we did here was to look at the effect of the cement alkali level and how it influences the expansion of these prisms. And what we did was for the top line here, this is the standard mix where we had a high alkali cement that's boosted to 1.25% soaked in a 1 normal sodium hydroxide solution. We made a couple of other companion specimens where the alkali content of the cement was different. This was a 0.82% alkali cement. We did not boost it. And when you actually figure out the hydroxyl ion concentration of a pore solution that you would get with that particular mix with this alkali level, essentially turned out to be about a 0.7 normal sodium hydroxide solution. And we used the predictive equation that was developed as part of Sharp C342 work that Helmuth and others had done. And they developed an empirical equation basically relating the cement alkali level, the water cement ratio, and predicted what the potential composition of the pore solution would be. And that's what we used in our study. And so our soak solutions for this specimen here and this one with two different alkali levels were 0.7, 0.45 normal. Nothing surprising here. The lower the alkali level, we get lower expansion. But this is as close to, I guess, avoiding the leaching, if you will, is to kind of have submerge the samples in a soak solution that is very similar to what the pore solution is made of. So you don't have any leaching. Flip side of it, that is that now you have a fairly large reservoir of a pore solution that is feeding into the sample as the reactions take place. But it's definitely a little bit more conservative than not having anything at all or doing other things. So we did that, and we measured the expansion at 56 days, and then we basically correlated the soak solution alkalinity to the expansion. And what we found was generally there's a very definite trend. This is the 28-day expansion with increasing alkali level. You get an increasing expansion. This is at 56 days. So we observe these trends again. So it's not surprising, but certainly significant in that if you change the alkali level of your field concrete, certainly your expansion can be quite different than if you had a standard test method with a standard alkali loading on it. Then we looked at the effect of water cement ratio with both high alkali cement and low alkali cement. And when we did this test, for each of these, we used soak solutions that matched with that predicted soak solution composition based on the predictive equation. And we really found that at least between 0.4 and 0.5 water cement ratio, there wasn't a whole lot of difference in how these specimens behaved. Well, obviously, with the lower water cement ratio, you have alkali enrichment, but also your pore structure and the mechanics of the concrete are different. And the same with low alkali cement, too. There's not a whole lot of difference with decreasing water cement ratio. These are pretty flat lines across both of those. If you look at the effect of cement content, we tested 3 different concrete mixtures with both the high and low alkali cements at 600, 700, 800 pounds per cubic yard. And we found that there is some influence, again, depending on what your cement content is. Your expansion can be different for both low alkali and high alkali cements. So that's another factor to consider. What we tried to do was kind of put the cement content and the alkali levels together and determine basically what the total alkali loading in the system was, and then plot that data against the 56-day expansion to see how all of that matches up. And when we did that, basically what we found was these shows a pretty linear correlation regardless of what alkali cement you use in the mix. It's really the total alkali loading. Again, this is not surprising. We all know that the alkali loading makes a big difference. So clearly there is a linear trend there in terms of alkali loading that supersedes any individual influences of either cement content or water cement ratio. All of those things can be expressed in terms of the total alkali loading. And these are the low and the high alkali cements, and they match up quite well. So if you look at the typical limits that we use in terms of alkali loading, about 5 pounds per cubic yard, that again matches up very well with the expansion limits that we typically follow. So another reassurance that it's possible. When you look at the coarse aggregate volume fraction, we looked at 0.65 or 65% to 70% of the coarse aggregate volume fraction in the concrete as part of the aggregate matrix. We saw really not a whole lot of difference. There was some with the higher alkali cement. This is with Sprat, and this is with another granitic gneiss aggregate. We saw that there was a little bit of increase, but not substantial. And again, with fly ashes, clearly the low lime or the class F ashes versus class C ashes, there's a big difference in terms of the dosage level and how it influences. So again, all these need to be captured in the job mix. In order to evaluate the performance of a job mix, basically what we devised is to run for the standard test as well as the job mix, a control test and a mitigation test. Pretty much every job mix has fly ash or some SCM in it. And so we developed a performance index of concrete, which is basically a comparison of the reduction in expansion between the control and the job mix with reference to the control. And you figure out what the performance index is, and that gives you a measure of how well your job mix is controlling the expansion compared to a control mix. So I have 2 quick case studies that I want to share with you here. These are real pavement mixtures. This is actually from a couple of airports. This is a taxiway at an airport, had a job mix that had about 40% slag. So essentially we got hold of the aggregates and cements that are very similar in composition. We tested them. And we found that if you didn't have the slag, it showed a substantial expansion. With 40% slag, we got very little expansion. So if you figure out basically the performance index of this particular mix, it's about 87% based on the equation I gave you before. And we have another case study. This was another pavement. That was the Tango taxiway. And we did the same thing, except here they used only about a 15% Class C fly ash, which is a recipe for disaster if you're trying to control ASR. And that's exactly what happened here. Really, there was no difference between the two. And if you look at the performance index of that job mixture, it was about 1%. So virtually there was no control on expansion. One possible way to specify something like this would be to determine the performance index of a standard mix with control and the job mix and the mitigated mix. And for the job, again, do a control and a mitigated mix. Look at these two values and have something. This is an example. I'm not trying to say this is it, but this is a way to look at specifying for job mixtures, if you will, based on a performance index. Just to conclude, like I said, certainly NCPD is not an answer to all the questions that were raised by previous speakers, but in the near term, while we are still trying to find the silver bullet, this is an option that we can look at that gives you a quick result, literally in about 8 weeks for most cases, where you get a reliable result than a motor bar test. It certainly seems to be a reliable and a rapid test method. We've studied well over 40 aggregates, so there is enough data to show how this works. And we looked at different mixture proportion variables like I shared with you. And it seems like certainly the alkali loading and the SCM dosage are the two factors that can make a big difference. The other variables are not as significant. And again, like I said, the preliminary testing and the performance index perhaps provides us a way to look at some of these options as evaluate the job mixtures. So with that, I'd like to end this presentation.